July 24, 1943. Zeist, Netherlands. General Josef Kammhuber stood before the plotting table in his command bunker, watching the green phosphorescent trace of RAF bombers crossing the North Sea toward Hamburg. The Kammhuber Line, his masterpiece of defensive engineering, stretched from Denmark to central France in a chain of radar stations that had cost the Reich over 50 million Reichsmarks to construct and equip. 3 years of meticulous planning, hundreds of Freya early warning radars, thousands of Würzburg tracking radars manufactured by Telefunken and the Zeppelin Company at enormous cost. A network of searchlights, flak batteries, and night fighters coordinated through dozens of Himmelbett control centers. Each defensive box covering 32 kilometers north to south, 20 kilometers east to west, precisely calibrated to guide Messerschmitt Bf 1 to 10 night fighters to their targets with mathematical certainty. Tonight, 791 British bombers were approaching Hamburg in the largest raid yet attempted. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Kammhuber's system should tear them apart. 6 interceptions per hour per Himmelbett zone, multiplied across dozens of boxes. The numbers were absolute, the mathematics unforgiving. RAF Bomber Command losses tonight should exceed 100 aircraft. But as the first Pathfinder Lancasters crossed into German airspace at 12:28 in the morning of July 25th, something impossible appeared on every radar screen from Heligoland to Hamburg. The single trace marking the lead bomber suddenly exploded into dozens, then hundreds, then thousands of individual returns. Cathode ray displays across the defensive network transformed into solid masses of light, tracking radars locked onto targets that weren't there. Master searchlights wandered aimlessly across empty sky while actual bombers flew overhead unseen. In Zeist, Kammhuber watched his carefully constructed defensive system collapse into chaos. Within minutes, radar operators shouted conflicting reports, night fighter controllers vectored aircraft toward phantom contacts, flak batteries fired blindly at altitudes where no bombers existed. The precise mechanical ballet of ground-controlled interception, refined through 3 years of combat, dissolved into helpless confusion. What neither Kammhuber nor his staff yet understood was that the British had just deployed a weapon that would render 50 million Reichsmarks worth of radar equipment nearly useless in a single night. Not through superior technology or overwhelming force, but through strips of aluminum-coated paper measuring 27 centimeters long and 2 centimeters wide, cut with household scissors by a Welsh physicist named Joan Curran, bundled into packets weighing 1 pound each, and dropped by the thousands from every aircraft in the bomber stream. Window, as the British called it. Duppel, as German scientists would recognize it when they found the metallic strips carpeting Hamburg the next morning. The simplest possible radar countermeasure, based on physics so fundamental that both sides had independently developed the concept years earlier. A cloud of metallized strips, each cut to half the wavelength of German tracking radars, creating false returns that transformed every radar display into an unreadable mess of overlapping echoes. The psychological transformation began in those first minutes after midnight on July 25th. German radar operators, who had spent years perfecting their craft, suddenly could not distinguish real bombers from electronic ghosts. Night fighter pilots, accustomed to precise guidance from ground controllers, found themselves directed to empty air while bomber streams passed kilometers away. Flak battery commanders, who had relied on radar for accurate fire control, watched their guns shoot blindly at incorrect altitudes, while actual aircraft dropped incendiaries unopposed. By 1 in the morning, Hamburg was burning. 1,350 tons of high explosives and incendiaries fell with devastating accuracy. The Pathfinder Force, using H2S ground mapping radar that the window Chaff did not affect, marked targets with colored indicators. The main force followed, their bomb aimers watching the markers glow through the rain of metallic strips still falling from aircraft ahead of them in the stream. Kammhuber's defensive network, which had typically destroyed 40 to 50 bombers per major raid, shot down only 12 aircraft that night, a loss rate of 1.5% compared to the typical 5 to 7% losses that had made RAF Bomber Command's campaign nearly unsustainable throughout early 1943. The exchange ratio had reversed catastrophically from Germany's perspective. What had been a war of attrition favoring the defense had become a massacre of the defenders' capabilities. German scientists examining the metallic strips the next morning understood immediately what they were seeing. The Reichsluftfahrtministerium, the Reich Air Ministry, had its own Chaff development program dating back to 1942. Research conducted at Düppel, an estate near Berlin, had produced working prototypes of what German engineers called Düppel strips. Testing had proven the concept viable. Production specifications existed. Small quantities had been manufactured. But Germany had deliberately chosen not to deploy the weapon for the same reason Britain had suppressed window until July 1943. Both sides understood that once Chaff was used, the enemy would immediately copy it and retaliate. British Air Marshal Arthur Harris and Professor Frederick Lindemann, Churchill's scientific advisor, had argued for months about whether the tactical advantage of blinding German radar was worth the strategic risk of giving the Luftwaffe a weapon that could blind British radar during renewed bombing raids on London. The decision to use window had come only after careful analysis of the strategic balance in mid-1943. By summer of that year, the Luftwaffe lacked the bomber strength to launch sustained attacks on Britain, even if they possessed effective countermeasures against British radar. Germany's industrial capacity was fully committed to fighter production, tank manufacturing, and replacing losses on the Eastern Front. The strategic air campaign over Germany had reached a critical phase, where RAF losses threatened to make continued operations unsustainable. Harris argued that window would save enough bombers to make the difference between success and failure in the campaign to destroy Germany's industrial capacity. The Chiefs of Staff agreed. On July 23, 1943, Churchill authorized immediate deployment. 24 hours later, nearly 2 million strips of aluminum-coated paper fell over Hamburg, transforming the night battle over Germany in a single stroke. The tactical effect was immediate and overwhelming. During the first window raid on Hamburg, each of the 791 bombers dropped one bundle of 2,000 strips every minute. Assuming each bundle remained detectable for 15 minutes, German radar operators faced the impossible task of distinguishing actual aircraft from 12,000 false targets simultaneously present on their displays. The Würzburg tracking radars, which formed the precision element of the Kammhuber Line, proved particularly vulnerable. Operating at 50 centimeter wavelength, the Würzburg used a 3-meter parabolic dish manufactured by Zeppelin and employed conical scanning for accurate target tracking. The system's sophistication became its weakness. Window strips cut to 27 centimeters created perfect half-wavelength resonance at Würzburg's operating frequency. Each strip reflected enough radar energy to appear as a valid target. Thousands of strips created thousands of targets, overwhelming the system's ability to track anything. The Freya early warning radars suffered equally catastrophic degradation. Operating at 1.2-meter wavelength with a range of 100 kilometers, Freya had provided the long-range detection that made the Kammhuber Line effective. Window strips created false returns that cluttered Freya displays to the point of uselessness. Operators could detect that something was approaching, but could not determine how many aircraft, at what altitude, or on precisely what course. The tactical picture dissolved into electronic noise. Even the improved Liechtenstein airborne intercept radar equipping German night fighters became unreliable. The Liechtenstein B divided by C operated at 55 centimeter wavelength, making it vulnerable to window. When night fighter pilots finally reached the bomber stream after being vectored to the general area by confused ground controllers, their own radar displays showed clouds of false returns rather than individual bomber targets. Visual acquisition became necessary, but the scale of RAF raids meant bombers were typically separated by several kilometers. Night fighters spent precious fuel searching empty sky while bomber streams passed through their patrol areas. The morning after the first window raid, Luftwaffe technical intelligence teams fanned across Hamburg collecting metallic strips from rooftops, streets, and parks. Analysis confirmed what German radar experts had feared for nearly 2 years. The British had deployed Chaff optimized for Würzburg and Freya operating frequencies. The strips were precisely manufactured to exacting specifications. The black paper backing prevented oxidation while providing structural support. The aluminum coating was applied with uniform thickness. Production quality suggested industrial-scale manufacturing rather than experimental batches. General Major Wolfgang Martini, Chief of Luftwaffe Signals, convened an emergency technical conference in Berlin on July 26. Representatives from Telefunken, GEMA, and every major German electronics firm attended. The discussion was brutally frank. Germany's entire radar-based air defense network had been rendered nearly obsolete overnight. Countermeasures would take months to develop and deploy. During that time, RAF Bomber Command would operate with impunity. The strategic mathematics were devastating. Germany had invested 50 million Reichsmarks in constructing the Kammhuber Line, thousands of Würzburg radars at approximately 100,000 Reichsmarks per unit, over 1,000 Freya radars at similar cost. The searchlights, communications equipment, control bunkers, and trained personnel represented years of industrial effort and technical expertise. Window had neutralized this entire investment using strips of aluminum-coated paper that cost a few pennies per kilogram to produce. Worse yet, from Germany's perspective, the British clearly possessed manufacturing capacity to produce window in unlimited quantities. The 2 million strips dropped over Hamburg on the first raid represented approximately 20 tons of material. If every RAF bomber could carry similar loads on every mission, Germany would face window deployment on a scale that no countermeasure could address. The industrial disparity between Britain and Germany meant that in a production race for countermeasures and countermeasures, Germany would inevitably lose. Martini's staff calculated that modifying existing radars to operate on different frequencies could provide temporary relief. If German radar operated on wavelengths for which British window was not optimized, the false returns would decrease. But frequency modification required redesigning transmitters, adjusting receiver circuits, and recalibrating antennas. For the Würzburg alone, over 3,000 units required modification. The industrial capacity and technical personnel necessary for such an effort would take 6 months minimum. Even frequency modification provided only temporary advantage. British reconnaissance could detect modified radar emissions. RAF technical intelligence could calculate new operating frequencies. Factories could cut window strips to new lengths within weeks. Germany would gain perhaps 2 months of improved radar effectiveness before British countermeasures caught up. The strategic balance had shifted permanently in favour of the attacker. The human cost of this technological defeat manifested immediately. Oberst Hans-Joachim Hermann, commanding a day fighter unit near Hamburg, watched the city burn from 20,000 feet that first night. He could see bomber streams silhouetted against the flames below, but ground controllers could not provide vectors. His radio buzzed with confused reports from Himmelbett centers. Radar operators reported hundreds of targets simultaneously. Night fighter pilots called for guidance that controllers could not provide. The coordinated defense that had cost Britain heavily throughout 1942 and early 1943 had collapsed into chaos. Hermann later developed the wild sow, wild boar tactic in response to Windows deployment. Since radar guidance had become unreliable, he proposed freelance interception. Day fighters would be directed generally toward bomber streams. Pilots would then hunt visually, using the fires burning below and searchlights stabbing upward to silhouette targets. The tactic required experienced pilots with strong night vision and considerable courage. It worked occasionally, but lacked the systematic efficiency of radar-directed interception. Loss rates for wild boar pilots proved unsustainable. Many crashed attempting night landings in unfamiliar fields. Others collided with friendly aircraft in the confusion over burning cities. The tactical innovations attempted after window deployment represented desperate improvisations rather than systematic solutions. Ground controllers directed night fighters to areas with the heaviest window concentration, reasoning that actual bombers must be nearby. This worked sometimes, but bombers began releasing window continuously along their entire route, eliminating concentration patterns. Fighters equipped with improved Liechtenstein SN2 radar operating at longer wavelength showed better performance against window, but production limitations meant few aircraft received the modification before war's end. Germany's attempt to develop radar operating at shorter wavelengths, specifically 10-centimeter systems that would require proportionally shorter window strips, absorbed enormous research effort with minimal operational impact. The Marbach fire control radar using 10-centimeter wavelength entered limited production, but manufacturing challenges restricted deployment to a few major cities. Even these modified radars provided only marginal improvement. British intelligence quickly recognized the frequency change and adapted window production accordingly. The second window raid struck Hamburg on July 27, 1943. 739 bombers attacked through solid window coverage. German defences shot down 17 aircraft, a 2.3% loss rate still dramatically lower than pre-window operations. The raid created a firestorm in Hamburg's eastern districts that killed an estimated 42,000 civilians and destroyed 60% of the city's housing. Temperatures in the firestorm reached 800 degrees Celsius. Winds generated by the thermal updraft exceeded 240 kilometers per hour. Asphalt streets burst into flame. People were swept off their feet and pulled into the inferno. The psychological impact on German leadership exceeded even the physical destruction. Albert Speer, Minister of Armaments and War Production, later told Allied interrogators that Operation Gomorrah, as the Hamburg raids were, codenamed, made an extraordinary impression on Hitler's inner circle. Speer stated that if the Allies repeated such attacks on 4 or 5 additional German cities, Germany might face strategic collapse. The implication was clear. Window had given the RAF the capability to destroy German cities with acceptably low losses to bomber crews. Hermann Göring, Reichsmarschall and Luftwaffe Commander-in-Chief, reportedly flew into a rage upon learning that the British had deployed a countermeasure so simple, yet so effective, that it negated years of German technical development. The 50 million Reichsmarks invested in the Kammhuber Line, the thousands of radar sets manufactured at considerable expense, the careful integration of flak, searchlights, and fighters into a coordinated system, all rendered inadequate by strips of foil dropped from aircraft. For the Luftwaffe radar operators and night fighter crews who had perfected ground-controlled interception over 3 years of combat, the window deployment represented something more profound than tactical defeat. It marked the moment when they understood that Germany was fighting enemies with industrial capacity and technical sophistication that exceeded German capabilities in fundamental ways. The British had solved the radar countermeasure problem that German scientists had identified, but German leadership had been too cautious to deploy. The Americans would soon join the offensive with even greater industrial resources. The strategic mathematics were becoming inescapable. Feldwebel Kurt Schwarz, a radar operator at a Freya station near Bremen, described the first window encounter in his diary with a mixture of technical fascination and personal despair. We watched our displays transform from precision instruments into useless toys within minutes. Years of training, thousands of hours calibrating equipment, hundreds of successful interceptions, all made irrelevant by strips of metal foil. The British had found a weakness so fundamental that no amount of German engineering could compensate quickly enough to matter. We understood that night that we were facing an enemy with resources we could not match. The tactical adaptation to window deployment occurred over months of painful trial and error. Ground controllers learned to ignore false returns and focus on persistent echoes that moved with aircraft-like velocity. This required experienced operators who could distinguish patterns in the electronic clutter. Training took time that Germany did not have. New operators faced overwhelming cognitive load attempting to separate signals from noise, while bombers overhead dropped tons of explosives with increasing accuracy. Night fighter pilots developed procedures for operating in window-saturated environments. The Zame Sau, Tame Bor tactic involved ground controllers directing fighters into bomber streams using the improved Liechtenstein SN2 radar, less affected by 50-centimeter window. Once in the stream, pilots hunted visually or used their onboard radar at close range, where individual returns could be distinguished. This worked better than wild-boar freelancing, but lacked the efficiency of pre-window operations when ground controllers could vector fighters precisely to individual targets. Flak batteries faced perhaps the most difficult adaptation challenge. Accurate anti-aircraft fire required precise range and altitude data that Würzburg tracking radars could no longer provide when wind saturated the area. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Batteries reverted to barrage fire patterns, filling probable bomber approach routes with shells at multiple altitudes. This was spectacularly inefficient in ammunition consumption and rarely hit anything. German flak crews fired thousands of shells to down single aircraft. The ammunition expenditure became unsustainable, even as bomber raids intensified through late 1943 and into 1944. The strategic implications of window deployment extended beyond immediate tactical considerations. RAF Bomber Command losses dropped from approximately 5 to 7% per mission in early 1943 to under 2% for window-equipped raids. This transformed the strategic bombing campaign from a marginally sustainable attrition contest into a decisive Allied advantage. Bomber crews, who had faced near-certain death after completing 15 missions, suddenly had realistic survival prospects through full operational tours of 30 missions. Crew morale improved dramatically. Aircraft shot down over Germany became statistical anomalies rather than expected outcomes. Bomber Command could sustain operations indefinitely at 2% loss rates, while training new crews faster than attrition eliminated experienced personnel. The strategic balance had shifted irreversibly in favor of the attackers. German industrial planners faced an impossible resource allocation problem after window deployment. Funds diverted to radar countermeasure research came at the expense of fighter production, tank manufacturing, and Eastern Front logistics. Every Reichsmark spent modifying existing radars was a Reichsmark not spent on weapons that might affect battlefield outcomes. Germany was fighting defensive battles on 3 fronts simultaneously, while attempting to maintain technological parity, with enemies possessing vastly superior industrial capacity. The decision tree facing German leadership after July 1943 offered no good options. Abandoning radar-guided defences meant accepting that Allied bombers would operate unopposed, destroying industrial capacity necessary to continue the war. Investing in radar countermeasures meant diverting resources from frontline combat while accepting that British countermeasures would arrive faster than German modifications could deploy. Either choice led toward eventual defeat. Kammhuber himself became a casualty of the strategic disaster. His advocacy for maintaining the Himmelbett system, despite its obvious vulnerability to window, conflicted with Hermann's wild boar and Sau tactical innovations. Personality conflicts with Erhard Milch, director of the Reich Air Ministry, provided political cover for Kammhuber's removal. In September 1943, he was transferred to command Luftflotte 5 inches Norway, effectively ending his influence over German air defense policy. The transfer represented more than personal rivalry. Kammhuber's removal symbolized the collapse of the systematic, technology-dependent defensive strategy that had characterized German night air defense through mid-1943. His replacement represented acknowledgement that Germany could no longer compete in the electromagnetic warfare domain, where British innovation and industrial capacity had established decisive advantage. The examination of Windows' effectiveness revealed uncomfortable truths about German technical capabilities relative to Allied advantages. British scientists had identified radar's fundamental vulnerability to chaff in 1941. Joan Curran, working at the Telecommunications Research Establishment near Swanage, had developed practical window prototypes in early 1942. She had tested various reflector shapes, including wires and sheets, before settling on the aluminum-coated paper strips that proved devastatingly effective. The development process had been remarkably straightforward. Curran cut strips of aluminum foil with household scissors at her home, calculating dimensions based on German radar wavelengths that British intelligence had identified through reconnaissance and captured equipment examination. She arranged the first field test at Christchurch Aerodrome in early 1942, having strips dropped from an aircraft while observers monitored radar displays. The effects were immediate and spectacular. Radar screens showed massive returns, suggesting entire fleets of aircraft where only a single plane with window existed. The simplicity was the point. Window worked not through sophisticated technology, but through exploiting basic physics of electromagnetic radiation. Any conductive material cut to half wavelength of incident radar would resonate and reflect that energy. The resonance was strongest at precisely half wavelength, but strips, even roughly approximating that dimension, would create usable false returns. Manufacturing required no advanced technical capability. Any factory with cutting equipment and aluminum foil could produce window in tonnage quantities. British production scaled rapidly once Churchill authorised deployment. Each bomber carried approximately 40 pounds of window packets, around 2,000 individual strips, bundled for easy handling. Crews dropped one bundle per minute throughout their mission, creating continuous false return clouds that persisted for 15 minutes per bundle. With hundreds of bombers in each raid, the cumulative effect saturated German radar displays completely. The production statistics illustrated Allied industrial advantages. British factories produced window by the ton. American factories joined production after analysing British specifications, adding their own massive industrial capacity to window manufacturing. By late 1943, window was available in effectively unlimited quantities. Bomber Command no longer considered conserving the material. Crews dropped window continuously from takeoff to landing, blanketing German radar coverage from British coast to target and back. Germany did attempt retaliation with its own Chaff deployment. 6 weeks after the Hamburg raids, on the night of October 7th to 8th, 1943, Luftwaffe bombers returning to operations over Britain dropped Duppel strips during a raid. The German strips measured 80 centimeters long by 1.9 centimeters wide, optimized for British chain-home radar operating at 12-meter wavelength. The deployment demonstrated that German scientists understood the principle and could manufacture effective countermeasures when permitted to do so. But the strategic context had shifted irreversibly. By autumn 1943, the Luftwaffe lacked bomber strength to sustain offensive operations against Britain. Germany's aircraft production focused almost entirely on fighters for homeland defense and tactical aircraft for Eastern Front operations. The few bomber units remaining operational could launch only token raids compared to the 1,000 aircraft formations RAF Bomber Command now routinely dispatched against German targets. Duppel allowed German bombers to penetrate British air defences with reduced losses during the limited raids attempted. Operation Steinbock, the mini-blitz conducted between February and May 1944, saw extensive Duppel use. German bombers struck London and other British cities, achieving tactical surprise through effective radar countermeasures. But the strategic impact was negligible. A few hundred bombers dropping tons of explosives could not match the destructive capacity of Allied 1,000-bomber raids that had become routine operations. The asymmetry was stark. British window deployment had neutralized a sophisticated defensive network representing years of German investment. German Duppel deployment achieved marginal tactical advantages in an offensive campaign Germany lacked resources to sustain. The industrial disparity between the combatants meant that identical technologies produced vastly different strategic effects, depending on which side deployed them. British countermeasures to German Duppel deployment were implemented swiftly and proved effective. The newer centimetric radars, equipping British defences by late 1943, were less vulnerable to meter-wavelength chaff that German Duppel represented. Fighter Command's chain of command adapted quickly, incorporating lessons from German experience with window, visual identification protocols, improved radio direction finding, and concentrated fighter patrols in probable approach routes compensated for radar degradation. More fundamentally, British air defence faced a threat of far smaller scale than German defences confronted. Intercepting 50 to 100 German bombers required far less precision than tracking 700 to 800 RAF bombers simultaneously. British controllers could saturate probable target areas with fighters and accept reduced radar effectiveness because the targets would likely appear somewhere within predictable zones. German controllers facing bomber streams that stretched hundreds of kilometres could not employ similar tactics without fighter forces exponentially larger than what Germany possessed. The German technical response to window focused on multiple parallel efforts, each consuming scarce resources with limited operational return. Telefunken developed Würzburg variants operating on different frequency bands, designated as islands in German documentation. Würzburg Island A through Island D covered discrete frequency ranges between 400 and 600 MHz. The theory was that British window optimized for standard Würzburg frequency would be less effective against modified radars. This worked briefly. Modified Würzburgs deployed in autumn 1943 showed improved performance against existing window. RAF bomber losses increased slightly during October and November, but British technical intelligence detected the frequency changes through electronic reconnaissance. New window strips cut to different lengths appeared within weeks. German radar operators watched their displays degrade again as British countermeasures caught up to German modifications. The frequency modification program illustrated Germany's technical sophistication and industrial limitations simultaneously. German engineers could design effective countermeasures. German manufacturers could produce modified equipment in limited quantities, but Germany could not scale production fast enough to equip the entire defensive network before British countermeasures appeared. The technological race was lost not through engineering failure, but through industrial capacity mismatch. Liechtenstein SN-2 airborne intercept radar represented Germany's most successful window countermeasure, operating at wavelengths between 3.7 and 4.1 meters, substantially longer than the original Liechtenstein B divided by C system's 55 centimeter wavelength. The SN-2 required proportionally longer window strips to create effective false returns. British window optimized for Würzburg and Freya proved less effective against SN-2. Production of Liechtenstein SN-2 began in mid-1943 with approximately 1,000 units manufactured by war's end. This was sufficient to equip a substantial portion of German night fighter force, but not enough to compensate for the broader defensive network's vulnerability. Night fighters equipped with SN-2 achieved better interception success rates than earlier radar-equipped aircraft, but they still required general vectoring from ground stations that remained blinded by window. The antenna system for SN-2 created additional complications. The longer wavelength required a larger antenna array, the distinctive Hirschgeweih or stag's antlers configuration mounted on the nose of night fighters. The antennas produced significant aerodynamic drag, reducing aircraft speed by up to 50 km per hour. Night fighter pilots discovered their aircraft were slower and less maneuverable with SN-2 antennas, making them more vulnerable to defensive gunfire from bombers and to Allied night fighter patrols. German scientists also developed Naxos, a passive receiver that detected emissions from British H-2S ground mapping radar. Since H-2S operated continuously to provide navigation and target identification for bomber crews, it created a homing signal that German night fighters could track. Naxos-equipped fighters achieved notable success during late 1943 and early 1944, downing bombers by following their own radar emissions to the source. But Naxos' success led to RAF countermeasures. Once British intelligence understood that H-2S emissions were being exploited, bomber crews received orders to minimize H-2S usage, activating the system only when necessary for navigation or target identification. Special H-2S variants with directional antennas that minimized side emissions were developed. The technological spiral continued, each countermeasure generating a countermeasure, with Allied industrial capacity ensuring they maintained advantage in the development race. The strategic bombing campaign intensified throughout late 1943 and into 1944 precisely because window had made operations sustainable. RAF Bomber Command launched the Battle of Berlin, a series of heavy raids against the German capital intended to recreate Hamburg's destruction on an even larger scale. Between November 1943 and March 1944, Bomber Command dispatched over 16 major raids against Berlin, dropping approximately 10,000 tons of explosives. Berlin raids proved more costly than Hamburg operations despite Window's continued effectiveness. The distance to target meant longer exposure to German defences. Berlin's size and dispersed layout made firestorm creation difficult. German defensive adaptations, particularly wild boar and tame boar tactics, achieved better interception success against concentrated bomber streams than the old Himmelbett system had managed. RAF losses during the Battle of Berlin averaged around 5%, significantly higher than immediate post-window rates but still sustainable compared to pre-window attrition. The culmination came on the night of March 30th to 31st, 1944, during a raid on Nuremberg. 795 bombers dispatched toward southern Germany encountered unexpected meteorological conditions. Bright moonlight eliminated darkness cover. Jet stream winds scattered the bomber stream across wider area than planned. German night fighters, vectored generally toward the stream despite window interference, achieved exceptional success through visual interception. 95 bombers were lost, representing a 12% loss rate, the highest single raid casualties Bomber Command suffered during the entire war. The Nuremberg disaster demonstrated that window, while dramatically improving survival odds, could not eliminate losses entirely. Determined defenders with sufficient aircraft and favorable conditions could still inflict catastrophic damage even when radar guidance was degraded. But Nuremberg was exceptional. The typical window-equipped raid throughout late 1943 and 1944 suffered losses around 2 to 3%, occasionally spiking to 5% under adverse conditions, but rarely exceeding that threshold. This represented the difference between sustainable and unsustainable operations. At 2% losses, Bomber Command could replace casualties and expand operational tempo. At 10% losses, the command would have bled itself to death within months. The most sophisticated application of window came during the D-Day invasion on June 6, 1944. Operations Taxable and Glimmer represented elaborate deceptions, designed to convince German coastal radar operators that major invasion fleets were approaching Pas-de-Calais and Boulogne, drawing attention away from the actual Normandy landing sites. Operation Taxable employed aircraft from 617 Squadron RAF, the elite Dam Busters unit. 16 Lancasters flew precise patterns off Cap d'Antifer, each dropping window on, carefully calculated schedules while flying at specific speeds and altitudes. The window deployment created radar returns, simulating a convoy of ships approximately 15 kilometers wide, advancing toward the French coast at 7 knots, the typical speed of invasion vessels. The deception required extraordinary precision. Each Lancaster flew an oval circuit approximately 8 kilometers long by 3 kilometers wide, dropping window bundles at precise intervals. As one aircraft completed its circuit and turned away, another began dropping window to maintain continuous returns. The overlapping patterns created the illusion of multiple vessels maintaining formation while advancing steadily toward shore. Operation Glimmer executed a similar deception off Boulogne using aircraft from 218 Squadron. The combined effect, reinforced by extensive electronic warfare jamming and small boats towing radar reflectors to simulate vessel movement, convinced German coastal defense commanders that two major invasion forces were approaching Pas-de-Calais precisely when the actual invasion fleet struck Normandy beaches hundreds of kilometers southwest. German coastal radar operators reported massive contact formations approaching at both deception zones. Wehrmacht commanders facing the Normandy invasion delayed committing reserves, believing the Normandy landings were diversionary attacks preceding the main assault at Pas-de-Calais. This strategic deception, achieved largely through sophisticated window deployment, contributed significantly to the invasion's success during critical early hours when Allied forces were most vulnerable. The technical sophistication of Taxable and Glimmer illustrated how far British understanding of radar countermeasures had evolved since Joan Curran's first experiments in early 1942. What had begun as crude tests with household scissor-cut foil strips had matured into precisely orchestrated electronic warfare operations, coordinating aircraft, ships, jamming equipment, and diversionary forces into integrated deception campaigns. German prisoners captured after D-Day described the psychological impact of facing an enemy with such comprehensive electronic warfare capabilities. Oberleutnant Franz Weber, a radar operator at a coastal station near Calais, told interrogators that German defenders understood they were facing opponents with technical advantages that rendered German equipment increasingly obsolete. We could detect that something was happening, Weber stated, but we could not determine what. Our radars showed contacts everywhere and nowhere simultaneously. We reported what we saw, knowing our reports were probably wrong, because we had no way to distinguish real threats from electronic phantoms. The broader pattern was undeniable. Germany had entered the war with radar technology roughly equivalent to British capabilities. By mid-1943, British innovation in both radar development and countermeasures had established a decisive advantage. By D-Day, Allied electronic warfare capabilities exceeded German defensive systems so comprehensively that German commanders could not trust their own intelligence gathering. The industrial dimension of this technological competition revealed the core asymmetry. British factories, supported increasingly by American production, manufactured window by thousands of tons. German factories, facing Allied bombing, resource shortages, and competing production priorities, struggled to produce modified radars in hundreds of units. The British could afford to waste window, dropping excessive quantities to ensure saturation coverage. Germans rationed every radar modification kit, installing them selectively on highest priority defensive positions. Albert Speer documented this disparity in his interrogations after the war. He noted that German industry devoted approximately 25% of ammunition production to anti-aircraft shells by late 1944. This represented enormous resource diversion from frontline combat operations. Much of that ammunition was expended in barrage fire patterns necessitated by radar degradation from window. The shells were manufactured at considerable expense, fired blindly at empty sky, and achieved minimal results. The resource allocation represented strategic defeat, masquerading as defensive activity. German radar operators interviewed by American technical intelligence teams after the war consistently described a progression from confidence to fatalism. Early in the war, German radar technology had been world-class. Operators took pride in their equipment's sophistication and their own technical expertise. The appearance of window in July 1943 marked a turning point. Operators understood immediately that they were facing an enemy with capabilities that German industry could not match. Obergefreiter Hans Zimmer, who served at a Würzburg station throughout 1943 and 44, described the experience in testimony recorded in June 1945. Window transformed our work from precision guidance to educated guessing. We tried various techniques. We tracked persistent returns. We ignored obvious false contacts. We coordinated with other stations to triangulate actual bomber positions. Sometimes these methods worked. Often they failed. The British seemed to have unlimited quantities of the metallic strips. Every raid brought more window. Our defensive network, which had cost millions to construct, it became a system for detecting that we were under attack without providing useful information about how to respond effectively. The adaptation process involved human ingenuity, attempting to compensate for technical inadequacy. Experienced radar operators developed intuition for distinguishing real returns from window false contacts. This skill required months to develop and could not be taught systematically. New operators joining the defensive network late in the war lacked experienced mentors to train them. As attrition and redeployment thinned the ranks of veterans, the quality of German radar operations degraded progressively as the war continued. Night fighter pilots faced similar challenges. Those who had achieved success before window deployment found their skills less relevant after July 1943. Visual interception skills became paramount. Pilots who had relied on ground guidance and onboard radar found themselves hunting in darkness with degraded electronics. The best night fighter aces adapted, developing techniques for operating in window-saturated environments. Average pilots achieved fewer kills and suffered higher casualties. Heinz Wolfgang Schnaufer, Germany's highest-scoring night fighter ace with 121 confirmed kills, exemplified successful adaptation. Flying predominantly in 1944, after window deployment, Schnaufer developed tactics that minimized reliance on ground guidance. He used his Liechtenstein SN2 radar to detect bomber streams, then closed visually for kills. His success rate was exceptional but not replicable by average pilots. German night fighter training could not scale to produce pilots with Schnauffer's capabilities in numbers necessary to offset Allied quantitative and technological advantages. The strategic endgame arrived in late 1944 as Allied ground forces advanced through France and overran radar stations that had formed the Kammhuber Line's foundation. The physical infrastructure that had survived Windows' electronic neutralization fell to conventional military operations. German defensive perimeter contracted toward the Reich's borders. Radar coverage gaps widened. Allied bomber formations struck targets across Germany with minimal losses. By January 1945, German radar-based air defense had effectively ceased functioning as a coordinated network. Individual stations operated independently, providing local warning without integration into larger defensive system. Flak batteries relied on visual acquisition and barrage fire. Night fighters hunted freelance, using whatever radar equipment remained functional and attacking targets of opportunity rather than executing coordinated interceptions. The final accounting revealed the magnitude of Windows' strategic impact. RAF Bomber Command flew approximately 364,000 sorties against European targets during World War II. Of these, approximately 130,000 occurred after window deployment in July 1943. Loss rates for post-window operations averaged between 2 and 3% compared to 5 to 7% pre-window. This difference represented thousands of aircraft and tens of thousands of aircrew lives saved. The campaign's effectiveness increased simultaneously with casualty reduction. Pre-window raids achieved limited damage due to defensive effectiveness, forcing bombers to take evasive action during bomb runs. Post-window raids achieved concentrated bombing patterns as reduced defensive effectiveness allowed more precise target approach. The combination of higher sortie sustainability and greater individual raid effectiveness transformed strategic bombing from a marginally viable strategy into a war-winning campaign. German industrial production statistics reflected the impact. Despite Speer's organizational improvements and dispersion of manufacturing facilities, German production of key military equipment peaked in mid-1944, then declined through war's end. Allied bombing, enabled by Windows' neutralization of radar defenses, destroyed factories faster than they could be rebuilt or dispersed. The strategic bombing campaign achieved its objective of degrading German military capacity precisely because Windows made sustained operations possible. Post-war technical analysis by both Allied and German investigators confirmed Windows' revolutionary impact. American and British teams examining captured German radar equipment found sophisticated hardware rendered inadequate by simple countermeasures. German technical reports recovered from archives documented the resource diversion necessitated by Windows countermeasure development. The documentary evidence supported operational results. A simple technology, deploying straightforward physics, had defeated complex systems through exploiting fundamental vulnerabilities. Joan Curran received limited public recognition for Windows development during her lifetime. The work remained classified until well after war's end. Her contributions were documented in official histories but not widely publicized. R.V. Jones, her colleague at TRE and later a historian of scientific intelligence, stated in his obituary tribute that Joan Curran made an even greater contribution to Allied victory than her husband Sam's work on proximity fuses. High praise, but delivered decades after the fact to audiences largely unaware of what Windows had been or how it worked. The broader lesson transcended individual recognition. Windows demonstrated that technological superiority emerged, not from developing the most sophisticated equipment, but from identifying and exploiting enemy vulnerabilities, using the simplest effective countermeasures. German radar was technically excellent. Windows was technically trivial. The trivial countermeasure defeated the excellent technology because physics was unforgiving, and industrial capacity determined who could scale production of countermeasures faster than opponents adapted. Germany's failure to deploy Duppel before Britain used Windows represented strategic caution prevailing over tactical advantage. German leadership feared British retaliation more than they valued offensive opportunities their own Chaff deployment might enable. This conservative approach made sense given Germany's strategic position. By 1942, when German Chaff development was mature, the Luftwaffe could not sustain offensive operations, even with radar countermeasures. Deploying Doppel would have given Britain justification to use window while providing Germany minimal benefit. Britain faced the inverse calculation. By mid-1943, RAF Bomber Command's strategic campaign was approaching unsustainability due to losses. Window offered a way to reduce casualties to acceptable levels. British Fighter Command and Anti-Aircraft Command had sufficient capability to defend against limited Luftwaffe raids, even if German bombers used Chaff effectively. The risk-reward calculation favoured British deployment. Churchill's authorization reflected this strategic arithmetic. The German response after window deployment revealed an industrial base already stretched beyond sustainable limits. Every resource devoted to radar countermeasures came at expense of some other military priority. Fighter production suffered as manufacturing capacity was diverted to modified radar equipment. Ammunition production for frontline units decreased as anti-aircraft ammunition consumption soared. Research personnel who might have developed improved aircraft or weapons instead worked on radar modifications that became obsolete before achieving operational deployment. This resource competition represented the true strategic impact of window deployment. Not merely that it blinded German radar, though that was significant. More fundamentally, it forced Germany into a technological race that diverted scarce resources from higher priority military requirements, while knowing that Allied industrial capacity would inevitably win any extended competition. German leadership understood this, but had no choice except to continue the futile competition. Abandoning radar-based defense meant accepting that Germany's cities would burn unopposed. The human cost on both sides illustrated the technology's significance through different mechanisms. For Allied bomber crews, window meant the difference between probable death and probable survival. Crew morale, recruitment, and operational effectiveness all improved when losses dropped below 3%. For German defenders, window meant frustration, helplessness, and awareness that they were fighting with inadequate tools against enemies who possessed decisive advantages. Hauptmann Wilhelm Jonen, a night fighter pilot who survived the war, described the psychological burden in his memoir. "We flew knowing that our radar might fail at critical moments. We hunted bombers through electronic fog created by their countermeasures. We watched cities burn below while we searched futilely for targets our equipment could no longer find reliably. The British had solved a problem how to blind our radar that our scientists had identified, but our leadership had been too cautious to exploit. That hesitation cost us the air war." The lasting legacy extended beyond World War II into the Cold War and modern era. Window established that electronic warfare was not merely supporting capability, but could be a decisive factor in military operations. Post-war air defense development prioritized countermeasures. Radar systems incorporated frequency agility, multiple wavelength operation, and sophisticated signal processing to resist chaff and other electronic countermeasures. Modern military aircraft carry chaff dispensers as standard equipment. The basic concept Joan Curran developed in 1942 remains valid in 21st century warfare. Contemporary chaff uses metallized glass fibers rather than aluminum strips and is deployed using explosive cartridges for rapid blooming, but the underlying physics is unchanged. Conductive material cut to resonant wavelength creates false radar returns that degrade tracking effectiveness. The technological spiral continues. Modern radars use complex waveforms, frequency hopping, and digital signal processing to distinguish real targets from chaff clouds. Modern chaff responds with broader frequency spectrum coverage and persistence-enhancing chemicals. The competition between radar and countermeasures that began with window deployment has never ended. Each generation of technology produces new capabilities that the following generation must counter. For historians analyzing World War II's technological competition, window represents a case study in asymmetric advantage. Germany invested 50 million Reichsmarks constructing a sophisticated defensive network. Britain invested perhaps £50,000 developing window, a rounding error compared to German expenditure. The cheap countermeasure defeated the expensive system because fundamental physics favored the attacker, and industrial capacity determined who could scale production most rapidly. The strategic bombing campaign's success depended on multiple factors: American daylight precision bombing, British night area attacks, improved navigation systems, better bomb sights, and escort fighter development all contributed. But window was perhaps the single most important technology enabling the campaign's sustainability. Without window, RAF losses would likely have forced operational suspension or dramatic scale reduction during late 1943. With window, operations intensified through 1944 and 45, destroying German industrial capacity and contributing significantly to Allied victory. The final irony was that both sides had possessed the technology since early war. Both had deliberately refrained from deployment for fear of retaliation. When Britain finally used window, German scientists immediately recognized what they were facing because they had developed identical capabilities themselves. The aluminum strips collected from Hamburg streets in July 1943 were indistinguishable from the Duppel strips German factories had manufactured in 1942. The difference was not technical but strategic. Britain deployed first because British strategic situation demanded accepting the risks. Germany responded because they had no choice, though their strategic situation meant Duppel deployment provided minimal advantage. The technological stalemate broke in Britain's favour not through scientific superiority, but through correct assessment of relative strategic positions and accurate calculation of risk-reward ratios. General Josef Kammhuber, watching his defensive network collapse on July 25, 1943, understood immediately that something fundamental had changed. His memoirs, written after the war, reflected on that night with mixture of technical appreciation and strategic regret. The British had solved a problem elegantly. They had deployed a countermeasure that German scientists had predicted and German engineers had replicated, but German leadership had been too cautious to use. The 50 million Reichsmarks invested in the Kammhuber Line had been neutralized by tons of aluminum-coated paper strips cut to specific lengths and dropped from aircraft. The lesson was unforgiving. In technological warfare between industrial powers, sophisticated systems created vulnerabilities that simple countermeasures could exploit. Victory emerged not from building the most advanced equipment, but from identifying enemy weaknesses and deploying effective countermeasures before opponents adapted. Industrial capacity determined who won the resulting competition. Germany had lost the electronic warfare race not because German scientists were inferior, but because German factories could not match Allied production scale. That realization, more than any battlefield defeat, convinced many German officers that the war was lost. Not merely that current battles were going poorly, but that structural advantages favoring the Allies made eventual defeat inevitable. Window demonstrated Allied technical sophistication, industrial capacity, and strategic thinking that Germany could not match simultaneously. Each alone might be overcome. Combined, they represented insurmountable advantage. The bomber crews who scattered window strips across Germany throughout late 1943 and 1944 probably did not contemplate these strategic implications. They simply knew that survival odds improved dramatically when window was used. One bundle every minute, dropped through the flare chute, creating false radar returns that confused German defences. Simple actions, repeated thousands of times per raid, accumulating into strategic effect that helped win the air war over Europe. The metallic strips drifted slowly to earth, glinting in searchlight beams, carpeting streets and rooftops, accumulating in gutters and parks. German civilians collected them as curiosities. Children played with the shiny strips. Scientists analyzed them professionally. Intelligence officers measured and photographed them methodically. All recognized that these simple aluminum-coated paper strips represented a revolution in warfare. Radar, which had seemed invincible in 1940, had been defeated by 1943 through strips of foil costing per pfennigs per kilogram to produce. The examination of one such strip by a German technical intelligence officer in Hamburg on July 25, 1943, represented a moment of clarity comparable to Oberstleutnant Wilhelm Runge, examining the cavity magnetron from Rotterdam in February 1943. Both examinations revealed that Germany was fighting enemies with technical capabilities exceeding German understanding. Both marked psychological turning points where confidence in German technological superiority collapsed into recognition that Allied innovation threatened to make entire categories of German equipment obsolete. The aftermath was mathematical. Window had transformed the air wars exchange ratio from unsustainable for attackers to unsustainable for defenders. The strategic bombing campaign, which might have failed in 1943 without Window, instead intensified through 1944 and 45. German cities burned, German factories stopped producing, German transportation networks collapsed. The campaign achieved strategic effects that operational bombing could not have accomplished had German radar-based defences remained effective. In the final accounting, Joan Curran's strips of aluminum-coated paper, cut with household scissors, and tested over English countryside in early 1942, contributed as much to Allied victory as any other single technology, not through destructive power like the atomic bomb, nor through sophisticated capability like cavity magnetron radar. Instead, through elegant simplicity, exploiting fundamental physics to defeat complex systems, using straightforward countermeasures that any industrial economy could manufacture in unlimited quantities, but only the strategically advantaged side dared to deploy first. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.